To all our guests, ladies and gentlemen, right now, I would like to kindly invite you to be seated and be comfortable. Get ready for an exciting, insightful day at the SSIA Summit 2024.
Measures aimed at reducing the emissions we produce. We are focused on developing a roadmap for our Scope 3 product-related goals, bringing together customers, partners, and other stakeholders. Together, we will make a significant positive impact on the environment and create a better world for future generations. Our power values lie at the heart of who we are as one ASMPT. They anchor our brand. They embody our identity. They represent the pillars of our culture and help guide how ASMPT employees conduct themselves. In whatever we do, ASMPT's success depends most of all on our people and our strong global teamwork marked by collaboration, consultation, and open communication. We also strongly believe that a diverse and inclusive workforce makes ASMPT a stronger business. That's why we are one team. We are equal. We are diverse. We are inclusive. We are ASMPT.
This internship was an eye-opening experience as I get to learn more than what the school had taught me. This internship taught me how to think on my feet while working with the other engineers as well.
My internship has been a really fun and enriching experience, and I also got to learn many new things that I probably would not be able to get to learn outside. Other than that, I also got to meet many different people from many different backgrounds, which I thought was really, really nice.
I learned a lot here in GF, and it was a transformative experience that has fueled my passion for the environment and sustainability.
It's been a fun journey along the way. The team here was very welcoming, they're very warming, and they let me be hands-on to projects here that let me contribute to the team.
Everywhere you look, there's proof that semiconductors are changing the world. They're enabling new technologies that help save lives, enhance access to education, and shape the future of business and computing. But as semiconductors become increasingly critical to our world, demands continue to grow for them to become smaller, more efficient, and more sophisticated. At Lam Research, we're innovating to meet this demand every day. We create machines that enable modern chip production and push the boundaries of what's possible. We partner with customers to boldly take on the world's biggest challenges while supporting communities and driving greater sustainability. From enabling atomic-level precision to breaking down barriers to collaboration, we're transforming our industry and creating the breakthroughs that make so many other innovations possible. Because at Lam Research, we know semiconductor innovation will change the world in ways we can only imagine. Now, let's prove it.
Hi everyone, a very good morning to all our guests today. Ladies and gentlemen, distinguished guests, a very warm welcome to SSIA's flagship event of the year, the SSIA Summit 2024. We're really thrilled to have you here with us today. Just like last evening, perhaps some of us have celebrated the Mid-Autumn reunion. Today, this morning, the whole day actually, I would say it's perhaps a reunion for the industry players in the semiconductor industry, isn't it? Thank you so much for taking your precious time to join us this morning. And I would like you to give yourself a big round of applause and also the summit a big round of applause, shall we? Come on, kickstart the day with a very warm applause. Thank you so much. I really love the smile and the bright, refreshing face that you have on your face right now. Amazing. And I do hope at this point of time you have already collected the complimentary magazines of SSIA, which is called The Voice. If not, later on, we do have some time during the break for you to pick out the copy of the magazine. All right, and indeed, we look forward to have you here with us, and it will be a very inspiring day today for sure. All right, ladies and gentlemen, let us kickstart the event, the Summit 2024. It is now my honor to introduce someone who plays an integral role in driving SSIA's vision and fostering unity, innovation, and leadership within the semiconductor ecosystem. And it's none other than, ladies and gentlemen, please join me with a warmest welcome for Mr. Ang Wee Sing, Executive Director of SSIA, on stage to deliver the opening address.
Good morning. Minister Catherine West, UK's Parliamentary Under-Secretary of State for Indo-Pacific. His Excellency Nick Mehta, British High Commissioner to Singapore. His Excellency Samir Neber, the Jordanian Ambassador to Singapore, SSI board members, industry leaders, partners, and friends. A very good morning. Welcome to SSIA 2024. It's almost like yesterday only that I was on stage giving a speech for 2023 Summit. So time flies, as we really progress through the year in 2024. SSI Summit has become one of our industry's most anticipated and important annual conference, focusing on mega trends and the future of our industry. This platform has steadily grown to reflect the evolution of the global semiconductor ecosystem. Over the years, the Summit has transformed into a truly global event, attracting industry leaders, innovators, and partners from all corners of the globe. This growth is a testament to the collaborative spirit within our industry, with delegations and speakers from all over the world, actively participating in discussions that shape the future of semiconductor. This platform fosters collaboration, drives innovation, and delivers key insights to support global semiconductor ecosystem. This year's theme is on synergizing silicon, pioneering the future of AI and quantum technologies. Now, I know there were lots of questions about why quantum. I think it is not about why, but when, because it underscores the profound intersection between semiconductors, artificial intelligence, and quantum computing. Semiconductor forms the backbone of these revolutionary technologies, enabling advancement that are redefining the entire industries and reshaping the way we live, work, and innovate. Our goal this year is to really connect these dots, explore how AI and the quantum technologies can be powered and scaled through semiconductors, and pave the way to breakthroughs that lead us to the next technological frontier. By leveraging AI and quantum technologies, we aim to foster and further enhance our industry capability, drive sustainable innovation, and most importantly, to position Singapore as a hub in Asia for excellence in these cutting-edge fields. We will explore the adoption of AI also in the afternoon, where industry leaders will take the stage to present more about that. Now, I would like to also welcome Rafael of Xanadu, Kok Tiong from National Quantum Office of Singapore. Now, there are little less known organizations, at least in the context of semiconductor, and I hope today we'll open up our eyes to knowing what the quantum strategy is for Singapore, and hopefully to collaborate with companies like Xanadu to further accelerate quantum introduction to the world. Now, looking ahead, 2025 promises an exciting year for our industry here in Singapore and the globe. I'm also thrilled to know that Semicon Southeast Asia will finally be back in Singapore next year. This will be a significant milestone for us, bringing more global attention to Singapore and on the vibrant semiconductor industry. My friends from SEMI will be here too, so for companies who are not yet participating in Semicon, let's say in Singapore, please reach out to them, yeah? We're also planning several trade missions to support our local companies in exploring international opportunities and expanding their reach. More details of this will be shared in the coming months. This initiative reflects our commitment to build a stronger, more connected semiconductor ecosystem here in Singapore, and most importantly, around the world. None of this would be possible without the support from our sponsors today. To the sponsors of this year's Summit and Semiconductor Dinner, I personally thank you on your unwavering support. Your contribution have enabled us to scale this platform year after year. And this continued growth demonstrates how united we are in attracting the brightest minds, nurturing the stronger local ecosystem, and most importantly, to celebrate our shared successes together. I also like to take this opportunity to welcome our delegation, foreign partners that joined us here in Singapore for this year's summit. Your presence is a testament to the importance of global collaboration in the semiconductor industry. Together, we can overcome challenges, seize opportunities, and collectively advance the global semiconductor landscape. We look forward to working closely to achieve our shared goals. As we embark on this exciting journey together, let us be reminded that the future of our industry is built on unity and collaboration. When we unite our strengths, we amplify our potential to pioneer the future. Let this be the guiding vision for this year's summit as we forge ahead, empowering innovation and shaping the future semiconductor, AI, and quantum technologies. Once again, I thank you all, and I wish you a fruitful and inspiring SSIA summit this year. Thank you.
Thank you so much, Wee Sing, for those insightful words. Indeed, starting to tone right for today's summit, a transformative day ahead today. And indeed, our leadership continues to inspire all of us to drive innovation and progress in this semiconductor industry. All right, ladies and gentlemen, coming up next is really a true privilege to welcome a distinguished leader whose work significantly impacts international relations and the semiconductor landscape. Ladies and gentlemen, with your warmest applause, please join me to welcome Catherine West, the UK government's Parliamentary Under-Secretary of State for the Indo-Pacific, as she today will deliver the keynote speech for all of us.
Thank you very much for that lovely, warm Singaporean welcome. And it's a real delight to be here and to see some of the stalls which are showcasing all the important work and the fact that it's been written in a very user-friendly way to explain to those of us who are not from a science background just how important the innovation is in this field. And Mr. Wee Seng and Ms. Tong, thank you so much for your work and for welcoming myself and Nick Mehta, the High Commissioner, here this morning. It would come as no surprise to anyone arriving at Changi Airport in Singapore, which is considered a global tech powerhouse, or that it's been named Asia's smartest city here in Singapore. And landing here on Monday, I thought could almost be a scene from the future. Robot chefs staffing the food halls, robot cleaners sanitizing the terminals, and a 37-meter indoor waterfall cooling the building, and an indoor rainforest. It certainly looks like the future and has a really exciting way of opening out those opportunities to green our future. I'm glad to have the opportunity to reflect today briefly on critical technology, in particular of semiconductors, and on the positive impacts this industry can have for the people of the UK, Singapore, and the world. The possibilities are really impressive, and I know that without semiconductor technology, I could not have flown here to Singapore. The pilot could not have navigated the precise location. The organisers could not have communicated online to gather us all here together. Could not even have checked the weather on my phone this morning on my phone. So I am really pleased to be here and to support this important event. And I bring greetings from the new government in the UK, Mr. Keir Starmer, and also David Lammy, the Foreign Secretary, because we're very keen to see science and technology at the heart of the new Labour government. The UK is ranked as Europe's #1 tech ecosystem, and Singapore ranks 5th globally for innovation, and these are impressive numbers, but what does it mean in reality? In collaboration, together with our other global partners, we should absolutely be making the most of our strengths together. Speaking of all things new, I must of course acknowledge the other support that we've had within our government, the administration resolutely focusing on nurturing strengths in science and technology, and it's so great to see so many UK colleagues from across our university sector here. Our university sector in the UK is one to be really proud of, particularly those who are teaching our youngsters about the importance of science and technology. So I thank them for making the journey here so that they can collaborate with others and our international partners in particular. And the UK is proud to include other companies such as ARM, Graphzone and Pragmatic, to name a few, and other UK companies, some of which are small and growing, others which are better known. With the world's semiconductor chip market expected to double in size within the next 10 years, the UK would be foolish not to be investing in this area. That's why we're making work to boost our strengths in everything from chip design and new material semiconductors to silicon photonics and advanced packaging. We're also keen to continue to make strides in AI and quantum through semiconductor research and development. And I'm very pleased that the future of these interconnected technologies have been chosen as the theme of this year's summit. We know what a vital role they're said to play in developing economic growth and in helping to solve some of the greatest challenges we face around the world. The UK's AI startup industry is ranked 3rd in the world, and we're home to companies like Google DeepMind, founded in London, and there's particular potential for AI to improve the landscape of chip design, which brings with it significant economic opportunity. The UK is also establishing itself as a pioneer in quantum, currently ranked within the top 5 countries globally in quantum technology. Like other countries leading the way in semiconductor design and quantum technologies, we're constantly considering how best we can transform the research expertise into economic and industrial success, while also ensuring their uses in society are ethical, sustainable, and responsible. Of course, to make the most of the promising synergies between these emerging technologies, we must also prioritise the synergies between our countries and the strengths we bring to the global table. The UK and Singapore share a long-standing friendship and partnership. Our collaboration is already strong across science and technology, something we'll hear more about later from Professor Graham Reed, who has championed collaboration between the University of Southampton and Nanyang Technical University here. The last 2 years alone have seen the signing of the UK-Singapore Strategic Partnership and the UK-Singapore Digital Economy Agreement. These are just 2 examples of our countries coming together to strengthen our collaboration in technology, and that will continue to underpin our work in semiconductors, quantum, and AI. I want to do a very quick shout out to the Newport team who are in the south of Wales in the UK because of their expertise and the cluster group which they've developed. Of course, we must not underestimate the importance of collaboration in the face of the challenges and risks that new technologies can pose. Our eyes are open to these challenges, particularly the need to diversify supply chains in chip markets. The Indo-Pacific region is, of course, crucial to these chains, given its concentration of key players in the sector, and we are clear that working with Singaporean industry and the wider region is the only way to address our shared concerns and leverage our strengths. Diversification is not easy, and there are, of course, numerous barriers to entering the market, both financial and technical. However, the UK is ready to engage, to work together and play our part in keeping markets open and resilient. As I conclude, I thought a comment made by Bill Gates, some of you may have heard of him, almost 30 years ago, when he said, "We always overestimate the change that will occur in the next 2 years, and we underestimate the change that will occur in the next 10. Standing in a room like this one, speaking to leaders in the technologies of the future, that rings very true. In semiconductors, in AI, in quantum, we're talking about technology with the potential to revolutionize medicine, to mitigate the climate crisis, even defend our democracies against cyber attacks. If done right, none of these things could come easily or quickly, and they cannot be achieved alone. The time is now for countries like the UK and Singapore, nations with rich histories in skills and innovation, to come together, to foster new discoveries, improve resilience, grow our economies, create highly skilled jobs, and together lead the way at the cutting edge of technology that underpins every aspect of modern life. Perhaps in another 10 years, it'll be a robot standing here at the podium speaking to you all. For my sake, I hope not. Imagine a world without politicians. But what I do hope and believe we will achieve by then is to have invested together in technology that has improved the global outlook on climate, health, jobs, and prosperity. Let's make that happen. Thank you.
Thank you very much, Ms. Catherine, for your keynote speech, and that your perspective on global collaborations have provided us with much to consider as we navigate the path ahead. Thank you so much. All right, ladies and gentlemen, coming up next, our next session will shed light on Singapore's ambitious national quantum strategy and its relevance to the semiconductor industry. Leading this discussion is someone at the forefront of these cutting-edge initiatives. Now, ladies and gentlemen, please join me in welcoming Mr. Ling Kyok Tong, Executive Director of the National Quantum Office, who will guide us through the opportunities quantum technologies present for our industry and how advancements in semiconductor can further accelerate and development of this technology. Ladies and gentlemen, your big hand please to welcome Mr. Ling.
So, a very good morning to everyone here today, and for our foreign guests, a very warm welcome to Singapore. And thank you, Catherine, for your opening speech. I like the parting line. We always underestimate the change in 10 years' time. You know, 10 years ago, I was a director in the Science and Engineering Research Council in the A*STAR, the Agency for Science, Technology and Research. I was asked to start up a program on quantum. I tell you, I said, what is quantum? And the closest link I had was a cat as in a CAT, and it was spooky. So it took me a while to come to a realization what this concepts in physics is all about. So with that as a sort of a light-hearted intro into my presentation, which is actually about sharing what Singapore is doing for quantum tech development, and also sharing with you our thoughts from the National Quantum Office on some of the possibilities that we can engage the semiconductor industry here in Singapore, possibilities in how quantum can enable semicon innovation, and then in a vice versa direction, how the semicon industry can enable and advance quantum tech development. Is this the next slide, really? Okay. So this is the cat and the spookiness that I was talking about. I'm not quite sure how many of us here are quite well tuned to the science about quantum and everything about it. But I don't think I'm fully qualified to explain all the physics behind it. I mean, short to say that quantum is actually the science of very small, to do things at atomic scale or at the scale of the photon. And some of the interesting phenomena that we see in quantum can be explained through a thought experiment like a Schrodinger's cat. Okay, in those days, I didn't have a ChatGPT to help me, and it took a while for me to understand what the Schrodinger's cat is all about in quantum. And that is the power of quantum, which is the countless possibilities that you can exploit at the level of atomic physics. And that's why it can give rise to a lot of endless possibilities. I leave it to you nowadays you have ChatGPT to go and find out what Schrodinger's cat is all about. And then the second part is about quantum entanglement. It is about how two particles can be connected and be connected at a special distance apart. So from an Einstein point of view, it was actually quite spooky. And we have actually exploited this phenomenon in quantum to realize some of these technologies that we are hearing so much about today. One of that is in the area of quantum computing, where we are actually unlocking a totally new paradigm of computing power. And in some publications you read, it is about the ability to even hack the RSA algorithms for encryption. And then at the atomic level, exploiting some of these quantum phenomena to help in the area of quantum sensing. You are actually going to realize sensitivities beyond the classical limits. And thirdly, in the area of quantum secure communications, how you can enhance data security with quantum key distribution devices. And thanks to Wee Seng for inviting me to this SSIA summit, because this came hot on the heels of our Deputy Prime Minister's Heng Swee Keat's announcement of our National Quantum Strategy for Singapore in late May. And in that National Quantum Strategy, we share our ambition, our plans for the next 5 years, and we are going to resource it with about close to $300 million of RIE funding, research, innovation, and enterprise funding. So the outline of my talk today will basically cover two parts. Like what Wee Seng said, I'm new to the audience here, so I want to talk a lot more about what this National Quantum Strategy is all about, our vision and our strategic thrust, and then maybe share with you my thoughts on what are the kind of synergy that we can have between the semicon industry and the quantum technologies industry, and then some of the possibilities that I can see happening. I think the theme for this summit is, in collaboration, we discover possibilities, and this is something that I wish to do here today. And also in my conversation with Wee Seng, we are going to follow up from this talk here today to have a closer touch point with the SSIA, maybe organize a focus group, a roundtable, where we can make concrete some of these possibilities that I'm sharing with you today. So the National Quantum Strategy is actually our next bound in quantum tech development. We are going to resource it with close to $300 million. And there are actually 4 funding initiatives inside this National Quantum Strategy. I will elaborate more for each of them later. And then just briefly as outlined, it talks about our flagship center for research in quantum in Singapore, the CQT, Center for Quantum Technologies. There's a continuation and added boost to our quantum engineering program. And then also our ambition to be able to design and fabricate our own quantum processor. And as with all things in the deep tech space, talent is very crucial. And we are starting up a National Quantum Scholarship Scheme. So the vision for the National Quantum Strategy, or in short, I call it NQS, is for Singapore to be a leading hub for quantum tech development, 1, and also deployment, 2, with a vibrant quantum ecosystem of industry and research. This is very important. Quantum cannot stay in the labs, in the research centers. It has to go out into the industry and be deployed for impact. And also, importantly, a talented workforce. all at the same time while ensuring our continued actual access to critical technologies of national importance. So it's a national strategy that is driven by the National Quantum Office, which I head. It's hosted in A*STAR, but it's a national platform that serves the whole of the ecosystem. And in partnership with the National Research Foundation, which funds us, as well as the National Quantum Strategy. And we report to the National Quantum Steering Committee that is co-chaired by very two eminent personalities, Professor Loh Teck Seng, who is the former CEO of NRF, and Mr. Kwek Kim Pui, who is the former Chief Defense Scientist for our Ministry of Defense. So essentially, in the National Quantum Strategy, we want to strengthen our basic research, continue to build our leadership, accelerate translation, and also build out and anchor a quantum industry in Singapore, develop international partnerships, and this is something that we definitely like to do with the United Kingdom, attract, grow, and retain world-class talent. So there are actually 4 strategic thrusts in our National Quantum Strategy. In the area of scientific excellence, there's the CQT, I'll elaborate. Then in the area of engineering capabilities, in the area of talent, and in the area of building out what we call innovation and enterprise partnerships. So what are we going to do with CQT? CQT has a very long history in Singapore. It started in 2007. At that time, it was a very bold decision by the Singapore government to invest in our first research center of excellence, and the topic selected was quantum. And this actually put us in a very good position because over the more than 17 years of having CQT with us in Singapore, we have built out a very huge pool of research scientists and engineers, and some of them have actually left and started out research groups and experimental groups also elsewhere around the world, and some of them have also joined the industry. So we have a very good network of CQT alumni all over the world. And what we're going to do in this National Quantum Strategy is that we're going to elevate it from just being a research center of excellence in the National University of Singapore to be a national level center. This is where we will now tap onto all the peaks of excellence in our universities, like Nanyang Technological University, also in the A*STAR. And all these leading scientists will be affiliated to CQT and form part of what we call the expanded CQT as a national level center. So we will harness the top expertise in our quantum ecosystem. Secondly, on the engineering capability side of things, we want to strengthen our sovereign capabilities and focus on the critical technologies development and anchor industry partnerships. So what we will do in the National Quantum Strategy is to create what we call focal points, where we will bring in the industry as well as the researchers together and end users with sophisticated problem statements to create solutions. And this is actually a win-win partnership because as the solutions are created, we have industry that can offtake these solutions, and these are actually tested on what we call very good end user problem statements that comes from the various verticals of our Singapore economy. Another initiative under the National Quantum Strategy is to continue to build our momentum for National Quantum Safe Network. We have done a test bid over the past few years, and this has actually given us a lot of traction working with both the public sector agencies interested in secure communications, as well as industries that are providing solutions and wish to test bid such solutions in Singapore. And taking off from here, my sister agency in the Infocom Media Development Authority of Singapore, IMDA, has actually taken it a step further and launched a pilot network with 2 telco service providers to run trial QKD services. The second initiative under the NQS is our National Quantum Computing Hub. This is the one that I was saying earlier. We are going to bring in our researchers in our ecosystem. It's a one-stop shop, it's a focal point. And we have industry partners who are coming in, A, to provide what we call on-premises quantum computing resources, or B, access to cloud quantum computing resources. And they also have researchers in their companies who are willing to work on complex problem statements. So we have the researchers on one side, the industry, and we're going to bring in end users. And for a start, we have prioritized a few important sectors for us, at least from a Singapore point of view. One is in the area of computational biology. And just recently, we signed an ecosystem-wide MOU with Quantinuum, one of the leading quantum computing companies, to actually embark on collaboration, working on problem statements relating to computational biology. And we very much look forward to that collaboration to give us good results. Second area was in the area of quantum for finance. And this, we are actually in discussions with our sister agency, the Monetary Authority of Singapore. They have just launched a $100 million grant to advance tech adoption in the financial sector. And they have identified through discussion with us quantum as one of the pieces of the translation program, in addition to AI and cyber. So very exciting days ahead, and we definitely hope to engage more of the industry in this space. And this is something that will be of interest to our semicon industry colleagues here. We also have a quantum federated foundry. We are actually federating all the necessary clean room facilities and semicon equipment that we have in the ecosystem to help our researchers in the quantum space quickly prototype, quickly scale up. And this is going to have a very close synergy with one of our recent big announcements in the semicon space. Or in short, we call it NISTIC, the National Semiconductor Translation and Innovation Center, where there will be a first port of call for us if we want to gain access to some of the semicon tools necessary for quantum tech development. And this is our ambition, the National Quantum Processor Initiative. I think at the end of the day, it's still important as a country for Singapore to be able to have our local capabilities to design and build quantum computers and critical components. And what we intend to do is to build on the strength that we have, our chances for success, the critical mass of researchers we have in two areas. One is in the area of trapped ions and in the area of neutral atom arrays. So these are the two platforms that we will focus our energy on, and we are going to have prototypes at gated points in the 3rd year mark and in the 5th year mark. But we're not forgetting the other technology platforms that are also quite important for us. For example, in the area of photonics, there will be a targeted current core, as well as in the area of control electronics. And then another program under the National Quantum Strategy is in the area of sensors. And this is something that can be quite relatively closer to market than the other things that we are talking about. So applying and leveraging quantum for position, navigation, and timing, PNT, in the area of sensing. And we do have a very good research group in NTU that works on gravimeter, and we are now actually deploying it for geothermal survey. So that's quite promising. And then also, lastly, in the area of biomedical imaging. And as I said earlier, talent is going to be a key enabler of our National Quantum Scholarship. And we do have plans to train 100 PhDs and 100 master-level quantum talent over the 5 years to meet the needs of both the research ecosystem as well as the industry. And at the end of the day, we want to continue to grow our vibrant quantum ecosystem. We have quite a number of startups in the various quantum pillars of comms, computing, as well as sensing. And we have more than 50 research groups across our ecosystem to get altogether in the universities as well as in A-Star. So now maybe move on to the next part of my talk, which is to talk about the possibilities that we can envisage. I must first say that this is not exhaustive. This is just some of the possibilities. Another thing I need to say that quantum tech is still at a nascent stage. There's a lot of more work that needs to be done. But from our point of view, these are some of the possibilities that we see right now. And that's why the conversation with SSIA will be going to be very important as we help to make concrete some of these possibilities. One of which is to use the power of quantum computing to actually go deeper into material science research. Secondly, the use of quantum sensors, maybe atomic accelerators, to look at some of the fault analysis that we have on wafers. Thirdly, quantum computation for optimized device designs. So we see quantum computing as a very powerful force for the discovery of new materials. You know, if you want to find and develop new novel materials with improved properties, quantum computing can actually be that kind of enabler for the semicon industry. The other thing is the supply chain for the semicon industry. We understand it to be very complex. There are a lot of moving parts. There are black swan events. And quantum computing can actually maybe solve some of these complex problems in supply chain management. In the area of quantum sensing, we are looking at improving fabrication tooling, where we use quantum sensors to enhance the stability and accuracy of the semicon tools, and then also enhancing defects detection in the wafers using quantum sensors like atomic accelerometers for precise inspection. So this is what I shared earlier is what quantum can do for the semicon industry. But we definitely are also looking to the semicon industry to help to enable some of these quantum technologies to actually have the semicon industry come in to help us design and develop both the control electronics and the CMOS, using integrated photonics to drive the miniaturization of some of these quantum devices and systems, integrated silicon photonics for QKD, quantum key distribution, and exploring fabrication of complete quantum experiments in a single chip. So I'll just share in the next couple of slides what I meant by some of these enablement that I look forward to seeing from the semicon industry. As some of you may know, to implement a quantum full-stack computer, you can actually go by different technology pathways, one of which is the superconducting qubit quantum computer. So some of you may have seen an actual superconducting qubit quantum computer. It does really resemble a chandelier with different layers. These different layers actually to bring down the temperatures to what we call cryogenic levels. So while the qubit is actually at the very bottom of it, which is the key engine, there's a lot of partnership that we require for the semiconductor industry to look at the control electronics, to look at the cryostats, to look at the cryoelectronics, and also to look at device packaging. So this is one area that we look to at the semicon industry. So the second pathway for implementing a full-stack quantum computer is the trapped ions approach. So if you enter into a research lab that looks at trapped ions, you'll see a lot of lasers on the optical table, directing the light. And you also see a vacuum chamber trapping the ions. So we actually definitely look forward to miniaturization, all this set up onto a chip, whether it's an on-chip ion trap or photonic integrated circuits for the communication part of it. So this is something that we look forward to. And thirdly, another approach to implementing a full-stack quantum computer is the use of photonics. And we can generate the light source, and also we can have the superconducting detectors. But what is needed is also the peripherals around it. Things like wafer scale foundry fabrication, the active components like the lasers and modulators. And later Rafael from Xanadu, maybe he can talk more about it. I'm not an expert. I think I better defer to him. And also device packaging and the fibers and the electronics. So at the end of the day, I just want to say that we are ready, we are open, we are building on a strong foundation of the investments in quantum over the last 17 years, close to 2 decades. We have created what we call national level focal points that we want to bring in our industry, whether it's in the area of quantum computing, the federated foundry, the quantum safe network. And we have, through the National Quantum Office, a well-coordinated ecosystem of researchers across the universities and A-Star that is very keen to work with you. So with this, I thank you for your attention, and I have a QR code if you wish to find out more or make inquiries or start some conversations with the National Quantum Office. There's a webpage for you all to link up with. So thank you very much.
Thank you once again, Mr. Ling, for your insights into Singapore's national quantum strategy and also within our semiconductor industry, offering us a glimpse of an exciting future, of course. Indeed. Now we're going to hear from an expert, ladies and gentlemen, all right, about quantum computing. And our next speaker comes from one of the leading quantum technology companies pushing the boundaries of what's possible in computing. We're excited to hear about their pioneering efforts to develop a fault-tolerant photonic quantum computer and the implications this has for the semiconductor industry. Ladies and gentlemen, with your warmest applause, please join me in welcoming Rafael Janik, Chief Operating Officer of Xanadu Quantum Computing, as he shares insight into quantum photonics meets semiconductors, Xanadu's path to fault-tolerant quantum computing. Jano, please. Rafael Janik, please. Yes,
Thank you so much for the invitation to be here today. I know we talked about underestimating the development over 10 years. I can tell you right now, the quantum industry does not have that problem. We've been promising that a quantum computer is 10 years away for the last 30 years. Hopefully I can convince you today that we'll have it in the next 10 years for sure. So Xanadu is a photonic fault-tolerant quantum computing company with a very straightforward goal to build quantum computers that are useful and available to people everywhere. That useful part is really doing a lot of heavy lifting right now. You've probably heard that there are many companies working on this goal. A lot of them have quantum computers available today. Unfortunately, none of those can actually do anything real to advance the promise of quantum computing. We've been working on this now for 8 years. We're headquartered in Toronto, Canada, and we have a little bit over 200 people distributed around the world, with the majority of those folks in our headquarter location. So to date, we've stood up 9 of those quantum computers and made them publicly available. These vary in different capabilities, but again, once they've been put online, though they were incredibly valuable tools for research and innovation, none of them were able to deliver on the promise of transformative impact that quantum is supposed to have. We don't only work on the hardware side, we also work on the software side, building one of the leading software frameworks called Penny Lane. And in fact, just 3 weeks ago, we held a quantum computing competition here in Singapore, where universities and academic institutions, students, postdocs competed to see who was the best in Singapore on that, and they'll be actually joining us at Xanadu sometime early next year to continue those research partnerships. And we also work on the applications. Maybe another little dirty secret of quantum computing is that though we know how to build these devices, we only know maybe how to do 3 different things with them once we've actually built them. One of them is breaking public key encryption, or in my case, stealing 1/3 of the world's Bitcoin once we build the quantum computer. But there are also applications in quantum chemistry and other areas that we actually need to continue developing. And we work with partners like DSO, Toyota, Volkswagen to actually develop these applications for early, near-term, fault-tolerant quantum computers. We don't do this alone, and especially on the hardware side, I'm going to say these are partners that we have announced publicly. There are many partners missing from that list that we hope to be able to announce soon. But on the fabrication side, we work with a large number of partners, mainly on the semiconductor side, to really solve some of our biggest problems. On the software side, we also work with large multinationals like NVIDIA and AWS, both to integrate their hardware in our software stack, as well as to help them bring quantum products faster to market. If you're familiar with AWS Bracket, there's been a great collaboration between Xanadu and AWS to bring those capabilities to customers. And also we work directly with quantum startups in order to help them accelerate their research. Companies like Horizon here in Singapore in order to accelerate the work that they're doing. So the promise of quantum computing is really broad. You might have seen slides like this before where we've promised that we're going to solve next generation batteries, make medical breakthroughs in curing cancer, discover new materials for carbon sequestration to solve the climate issues that we are facing now. All of this hinges on the fact that quantum computing is an incredibly broad technology. When you think about quantum computing, you should be thinking not necessarily making an equivalent with AI, but much more so with digital computing. This is an enabling technology that is going to be as transformative as digital computers were in the 50s and the 60s, or as the internet has been through the 90s to current times. In order to deliver on that promise, we do need to really increase the capabilities of the devices we have today. At Xanadu, we stood up our first quantum computer back in 2019. This was an 8 squeeze mode qubit device. And more recently, 2 years ago, we actually deployed one of the world's most powerful quantum computers with a 216 squeeze mode qubit device called Borealis. This is that device. You'll notice that it was not fully chip integrated. This was still a bulk optics device. But uniquely, if you wanted to actually simulate this device to carry out the calculation that it was able to carry out on the world's fastest supercomputer at the time, Fugaku, it would have taken all 7.6 million cores, 7 million years to actually run that calculation. If you want to think about the energy costs of that, it's really ridiculous, 1.8 billion gigawatt hours of energy to perform that calculation. Now on our quantum computer, we are able to do that in 2 minutes with just 200 watt hours of power. Now the big caveat with this is that nobody cares about this specific calculation. This is not yet something that you will use in everyday business. And the goal is, how do you get the same advantage, the same transformative impact for real world business problems? And the way you do that is to not only change the architecture of the quantum computer to ensure that any errors that come into the calculation as you carry it out are able to be corrected, but also to drastically scale up the quantum computer itself. So in the first 8 years of our company, we really focused on the core optical components, on-chip components that make up our device, analogous to essentially building better transistors for our architecture. Now, over the last year, we really perfected the individual module. So this is the unit cell that will eventually go into our quantum data center. And now the future holds for us is improving the performance of that individual module to get it to a manufacturable state and actually deploy a large-scale quantum computer data center with thousands of logical perfect qubits that are made up of millions of physical qubits that we talk about today. And this really is not a huge data center when we talk about data centers. This is several thousand to tens of thousands of square feet. Think of about a football field. And this really will be the first time that you'll have that truly transformative impact of quantum computing available to people everywhere. We're not doing it alone. The race truly is on now in terms of developing this technology. Hopefully I'll be able to convince you why photonics is a platform that makes the most sense. But really any one of these technologies just relies on the ability to control matter at its smallest scale. In the case of superconducting circuits, which we already heard about, this is really about being able to isolate electronically current in really tiny circuits and be able to control it with incredibly high precision by manipulating it with microwave radiation. Ion traps and neutral atoms suspend individual atoms and allow you to control them with pulses of laser light, again, isolating them from their overall environment. And spin qubits look at being able to control individual atoms on silicon substrates in order to actually manipulate their spins either electronically or through light and be able to connect them together. All of these approaches have their own advantages and disadvantages. Some of them can make really phenomenal qubits today, like the ion traps, but the path towards building a system of millions of qubits is really challenging. Or vice versa in the photonics approach, where we understand how to scale these devices, but building these initial qubits is actually quite difficult. What maybe one thing I'd like to address is that each one of the challenges that we face in these architectures is actually a semiconductor challenge, whether it be on the fundamental materials that we are able to bring into foundries and work with them, or whether it is with the quality of materials we're able to grow, or actually how we pattern them directly on the chips, not being of sufficient quality today. Photonics does have pretty substantial benefits over some of the other approaches. The pain that we pay for these benefits is in fact in that if you ask somebody even several years ago whether there was a meaningful way to build a qubit on a quantum photonic platform, they would have identified very big challenges. Through the work done by both academics and companies like ourselves, this has been advanced over the last 8 years pretty drastically. The major advantages of quantum computing photonic-based platform is actually that it is manufacturable. We can leverage the billions of dollars that have been invested in the telecom and datacom industries and not have to recreate many of the building blocks. On top of that, our approach, not all photonic approaches, but our approach doesn't require cooling. All the computation can actually happen at room temperature, and these devices can be made data center compatible. They have faster clock speed compared to some of the trapped ion and neutral atom approaches, and there's also the ability to interconnect individual chips together by fiber optics. This is really important because today we don't really know how to build a 1,000,000 qubit device on a single chip or a single die. So this is something that we know we're going to have to do in a modular fashion. And photonics currently is the only one that has showcased high enough fidelity in interconnects to be able to do this out of the box. There are other technical advantages such as error correction flexibility, but maybe it's a little bit too deep to get into. If you'd like to learn more, I'd be happy to do a deeper dive with you maybe over lunch. So as I mentioned, a lot of these difficulties actually come down to semiconductor challenges. Today we are working on 3 platforms. Silicon nitride is the platform that we use for our state generation, so how we actually make our qubits. Thin film lithium niobate is the current platform that we're looking to explore for active switching, so being able to send our qubits into the different locations that they're needed. And then we use 3-5 semiconductors for our readout. So these are photodiodes very similar to what you would use in the automotive industry for LiDAR systems. Luckily, we don't need incredibly high bandwidths, but like with everything in quantum computing, we do need incredibly high efficiencies. These are maybe the notable problems that we're facing today in qubit synthesis, in optical networking, and in the application of our gates. But some of these problems are quite well on their way to being solved. So for example, on the silicon nitride platform, we've already been able to improve, depending on the components, the core metric, which is our source of error, being photon loss, by factors of 4 to 20. We still need a long way to go on many of those, but it's been pretty substantial steps forward. We do need one cryogenic device within our quantum computing architecture. This is a photon number resolving detector, a superconducting transition edge sensor that is able to tell us precisely the number of photons that have been detected on any specific channel. And there we've worked with the National Institute of Standards and Technology to actually push that technology forward quite aggressively, and actually been able to move that out of the NIST foundry and over to VTT, a Finnish microelectronic fab that are now doing that work at scale for us. Also, because the cryogenic requirements of photonic quantum computing are much lower, the cryogenics doesn't actually represent a very big issue. We can work with standard cryogenic suppliers like Blue Force today, and the footprint represents less than 10% of our overall data center. I also mentioned optical networking. Aspects of phase locking and polarization stability have been resolved on our large-scale systems. And for the gate application and error correction, much of the feedback loops that we need, the classical control electronics are already working at the rates that we need them. Where we really need help, I'm going to say fundamentally, is in one place. And this is dealing with photon loss. So as light travels through our photonic quantum computer, it goes through multiple chips, through many, many meters of fiber. And at any given time, a photon can scatter or be absorbed by the material. And this is fundamentally our major source of error. We can deal with some photon loss throughout that quantum computer, but right now, this is what we're aggressively working with our partners and pushing down. For example, on the low-loss silicon nitride photonic integrated circuits, we need losses of less than 1 decibel per meter. This is already orders of magnitude higher, or lower, I should say, than anything that is commercially available. And we've been pushing quite aggressively with our partners to bring that down as low as possible. Another area where we've been working quite aggressively is on the chip-to-fiber interface. So this is how do you actually connect fiber optic cables to chips without losing much of the light. Similarly, we've been pushing on novel platforms for fast switching while maintaining that incredibly low loss. And we're doing some really exciting work now on lithium niobate waveguides for active control of our routers. The other aspect where we definitely need help is just on the scale of what this device will look like. I mentioned that this is, several thousand square feet. You don't necessarily think of it as being very large, but when you start thinking of the number of individual components, it actually starts to get pretty scary pretty quickly. When we talk to our algorithm developers, they say the first real applications in quantum computing will require about 1,000 logical qubits. So when we talk about solving that computational biology problem or that quantum chemistry problem, what the algorithm developers are really looking for are qubits that can perform multiple operations without losing the information that they hold. We know that with current overheads and our best guesses on how much we'll be able to improve over the next few years, this represents about 1 million qubits. In our architecture, and I would say similarly for other architectures, this starts to come down to tens of millions to hundreds of millions of individual components that are required on millions of individual integrated circuits. And when you start talking about wafer volumes, this very quickly gets even scarier when you look at the type of yields that we're currently getting in the quantum space. I know that for many semiconductor people, this might not look like large wafer volumes right now, but when you start talking to people doing silicon photonics, this exceeds what is currently done in this silicon photonic space by datacom and telecom applications. So we'll definitely need much, much larger capabilities in order to be able to deliver on the promise of quantum computers. The news isn't all bad. All the work that we've done is actually now making it back into the semiconductor industry. So one thing I really wanted to highlight is the fact that on the passive devices on silicon nitride platforms, we really have world-breaking low loss numbers. And now this is actually now making back into PDKs with some of our foundry partners. We tend to work directly on the process level as well, as do many of our competitors and peers, meaning that not only are we advancing what can be done on the quantum side, but also on the classical side. Similarly for interconnects, chip-to-fiber interconnects, this is an area we've been able to push down so aggressively that now we're running into problems with test and measure and being able to effectively measure the losses across those components. And this has now garnered a lot of interest from classical partners in both the defense space and in the datacom space, as they're starting to look at metrics like picojoules per bit transferred as a key metric that they're driving forward. So we're already partnering with a few companies in order to take the advances that we've made for quantum computing, but apply them for other purposes in the classical datacom and telecom space. The other aspect that we've really, I would say, accelerated forward quite aggressively is the development of AI tooling for chip design and fabrication process engineering as well. Happy to talk more about the tools that we have in-house. This is something that we've currently kept proprietary to our own projects, but we are starting to think about how the classical world can actually start using these type of approaches as well. And all of this has actually culminated in a project that we called Field the Burn for last year, but now we call Aurora, and it's a new quantum computer that will be coming online in the next couple weeks. Hopefully you'll be able to read about it in a high-profile scientific publication. We're just going through the peer review process. But this is really the demonstration now of our fully modular architecture for a fault-tolerant quantum computer. The top chip that you see up there is a fully integrated source chip. So these are squeezers on a silicon nitride platform with interferometers. We have 84 squeezers across 24 chips working together. At each clock cycle, these generate a state of light, and with some probability, they generate specifically the type of quantum state that we're looking at. In order to boost that probability, they go into a MUX. So this is actually now fed forward with information from our cryogenic detectors in order to boost the probability of generating our quantum state of interest. That then moves into our fiber delay line once again in order to allow for the routing of our qubits to create the type of quantum state that we require, our cluster state. And then on the bottom, what you see is our QPU that has actually a series of photodiodes that allow you to perform the quantum computation that the user desires. Now, this is a small scale, but now fully integrated version of what that module that will go into the large-scale data center will actually look like. We have hit several very key important metrics around the ability of this to run in a steady state fashion, being phase locked without any sort of human intervention. But none of these components are yet of the performance that we need in order to demonstrate error correction and fault tolerance, the other two key aspects that we need. So really our goal with our manufacturer partners now over the next 2 years will be to work on each one of these individual subsystems, each one of those components, the interconnects, in order to reduce losses by anywhere from a factor 2, and some of them where we're pretty close to factor 10, and some other places where it's becoming a little bit more challenging. With that, I'd like to thank everybody once again for listening. Very happy to take any questions afterwards during the lunch session and do deeper dives on any part of the stack. Thank you so much.
Thank you so much, Rafael. That's right, later on we're going to have a panel discussions, and I'm sure there will be a lot of questions coming in. And looking forward to that. Thank you so much for your sharing. All right, we're going to have a little break coming up shortly, but before that, let us head on to next exploring the transformative potential of a technology that is shaping the future of communications, healthcare, and beyond, the silicon photonics. And our speaker is a renowned expert from the University of Southampton, an institution at the forefront of early-stage research and development in this field. Please, ladies and gentlemen, join me with a warm applause to welcome Professor Graham Reed as she presents silicon photonics and enabling technology, its key role in advancing UK national strategies in semiconductor, quantum, and telecommunications. Over to you.
Thank you very much, and thank you very much for the invitation. It's a pleasure to join you today. I am here as part of a UK delegation talking to some of the stakeholders in Singapore. They are sitting mostly at tables 33 and 34. Some of us seem to have been spread around. And it's a very talented team, and so I would encourage you to engage across all aspects of semiconductors if you get a chance. But my job is to talk to you about silicon photonics. It was very much a surprise and a pleasure to hear the minister utter the words silicon photonics. I didn't expect that. She also pointed out that I have a relationship with some of the folks in Singapore in terms of collaborations. Always interesting to know the government knows more about you than you thought. So that was interesting too. And furthermore, the previous speakers have all mentioned silicon photonics. And so they've partly done my job, because I think my job was to convince you that silicon photonics is an enabling technology, not really just for quantum and AI, but for many new applications right across semiconductors. Let's get started. The minister did mention, as I say, the link. Perhaps something she didn't say is that My group's been involved in silicon photonics right from the very beginning. We started out in 1989, so I think we're regarded as one of the founding groups of the field. We've tried our best to stay at the forefront of that technology ever since, and I think it's probably fair to say that we've done that to some extent. And so now we're looking at moving into some of the emerging applications, and this is where I think it's exciting. So I wasn't sure that everyone would even know what the word silicon photonics meant in the room, so I did include a couple of slides just to introduce the technology to you. But as I say, the previous speakers have done a great job in helping to do that. But basically, we can contain, manipulate, direct, and signal process light signals in a silicon chip. The waveguide dimensions vary from application to application, but the most popular dimensions are of the order of 200 nanometers. So even that is really sort of almost an order of magnitude smaller than, say, a typical optical fiber, which people would largely refer to as something of the order of a human hair. So the devices are very small, and it means you can get a lot onto a chip. In the early days, silicon photonics really just meant silicon itself as the guiding platform. But as you've just heard from Xanadu, there are now other guiding technologies. Silicon nitride is a very popular one. But more and more other materials are being incorporated into what is called silicon photonics as a platform. And so the whole technology is evolving and continues to do so. So already, silicon nitride, germanium are very common, but other materials are starting to be talked about. And we heard that thin film lithium niobate might be of interest, and there are many others too. And so heterogeneous integration of materials is very much a topical subject for the technology. So just a few pretty pictures to show you some of the sorts of components that you can put into a silicon photonics circuit. Obviously, the basic technology is based around the waveguides and being able to manipulate the light to the parts of the chip that you want. In some of the more recent applications, we might think about doing wavelength analysis, spectrometry, and so on. Multiplexers are now routine. Modulators, integrating electronic drivers and potentially amplifiers and detector amplifiers at the other end, getting lasers on chip, and coming into very complex circuits and so on. So that's the sort of technology as it is today. I just want to take a few slides to talk about the importance of photonics in general to the UK. And so this is a slide that I've borrowed from a group called the Photonics Leadership Group, which is a group of experts in the UK who essentially advise government. And this particular graph is a comparison of the states of technology between 2018 and 2021. And the plot is showing you turnover on the vertical axis versus employment on the horizontal axis of various sectors within the UK. And you see the one with the little red arrow is showing silicon photonics, even over the period of COVID, actually grew, both in terms of turnover and employment, whereas most other regions were contracting. Similarly, in terms of employees, the photonics industry, and this is not just semiconductors, but includes all of photonics, but is bigger than pharma, for example. That's perhaps a surprise in the UK in terms of employees. And in terms of revenue, is sort of getting on to the order of some of those major technologies like aerospace, pharma, and so on. So some interesting statistics, and it demonstrates the importance of photonics to the UK economy. And I think the reason that's potentially not obvious is because photonics is an enabling technology that's sort of behind the scenes in many products and services. And so you don't even realize that photonics is involved sometimes. In terms of distribution around the UK, you can see that there is interest and work going on around the UK, right across the UK. The output is in excess of $15 billion, so an important technology for the UK. various regions, significant output, significant employment, and a lot of companies in photonics in the UK. And the number of companies is large, particularly because they are mostly, or they're dominated by SMEs. So relatively small companies who have their own challenges in how to access technology and that type of thing. So that's interesting. But the statistic that I'll point you to is the one at the bottom of the right-hand side of that page. And that is that 50% of UK photonics companies invest more than 10% of turnover in R&D. So potentially that makes those companies potentially good partners for innovation, especially for universities, but also for other SMEs and perhaps even other parts of the supply chain. So that's an important point to make. Now, here's a plot from Yole. This is a little bit dated because it's 2021. But I wanted to show you this to demonstrate that the applications in silicon photonics are not just transceivers. There are lots of emerging applications. And I'll come back to this when I talk a little bit about our own work at Southampton. But notably, on this list, you don't explicitly see quantum and AI, actually. And that's because of the explosion in interest in those technologies, I think, in more recent years. But this is also about what's reaching the commercial environment. So, of course, that's all in the pipeline. But you see already important applications of silicon photonics that are not communications applications. And particularly for those of us in the research environment, these represent significant opportunities. And so when we talk about the opportunities of collaboration, not just between UK partners ourselves, but part of the reason that this delegation's here is to look at collaboration with folks in Singapore, these represent opportunities, I think, for all of us. And there are good complementary synergies between what's going on in Singapore, what's going on in Singapore and what's going on in the UK. And so I'll come back to that point a little bit later. So what about manufacturing? This is a slide that I've borrowed from friend and colleague Roel Batz at Ghent. And it shows you the various types of foundries that you can access for fabrication. From small volume R&D right through to the integrated device manufacturers and so on. And I think the surprise in some ways is that the number and range of opportunities there are across the globe. And one of those is at Southampton, and I'll tell you a little bit more about that later, because it's evolved in a somewhat surprising way in many ways. So, why is silicon photonics interesting? I think the thing that's really driven the evolution of silicon photonics is the transceiver market for data centers. This has really demonstrated the technology can exist in a commercial environment. And more recently, the advent of AI and the demand for more processing means that co-packaged optics is becoming more important. And of course, silicon photonics is going to play a key role in that area too. So I guess the message there is that silicon photonics is here to stay, and it can be an enabling technology for many of the applications that you may be working on, but perhaps you don't even realize that. I think, as I say, the previous speaker has done a great job in convincing already that silicon photonics is viable for quantum and a great scale-up platform for quantum. But I'll come back to that and a little bit about AI later. Before I do that, let's just think about the relevance for the UK. So like other countries, the UK has a national semiconductor strategy, has a national quantum strategy, and at the moment is looking and consulting on all aspects of telecom. So there are various expert working groups in the UK. I'm part of a telecoms working group. There's also a semiconductor working group looking at telecoms, which some of my colleagues are on. But the important outcome of that from my perspective is that all of the experts in those areas are citing silicon photonics as a key enabling technology. And so again, silicon photonics is here to stay. Thinking of things like the CHIPS Act that are sort of jumping up all over the globe. The USA is going big on silicon photonics. Europe is currently looking at silicon photonics pilot or photonics pilot lines in general, incorporating silicon photonics. Japan, Korea, and of course, I didn't put on here deliberately because I thought other people would talk about it, what's going on in Singapore. And it's good to see in some of our visits that silicon photonics is playing a key role in the future of Singapore as well. So, turning to what we do at Southampton, as I said, we've been in the field for a long while, and of course we've worked in telecom and datacom. But I don't think it's the job of a university, once a technology is commercialized, to be doing the sort of latter-day development. That's the job of the larger companies who are doing those types of things. I think it's important for us to do on some of that work where we can really make a difference in terms of the technology and where we can bring on new technologies, which is why we're working in all of these emerging areas as well as the telecoms area. So for example, at the bottom left, there's healthcare and environmental sensing. A lot of that needs to be done at longer wavelengths, so we need to start developing new waveguiding platforms even. Silicon on an insulator runs out at about 4 microns, but we need to get right out to potentially 15 microns, so we can look at undercutting silicon. We can look at using germanium and undercutting that. We can look at using germanium on silicon and other devices and platforms that take you out to longer wavelengths. There's an interest in going to shorter wavelengths. This is where I think silicon nitride comes in. And some of the quantum applications that were mentioned, you know, even the non-photonics ones, so for example, the ion traps where you need specific wavelengths to do the trapping, those wavelengths, if you want to deliver them, can be delivered on an integrated photonics circuit, perhaps in nitride. So there are even directly photonics applications into quantum that can be serviced by the silicon photonics platform. I guess LiDAR is becoming more known in automotive, but there are lots of other imaging applications of LiDAR as well. Computing and quantum, I probably don't need to mention to this audience the importance of getting the photonics closer to the electronics in those areas. And heterogeneous integration I've mentioned already in bringing those other areas together. Some elements of AI can be delivered directly into photonics using parallel processing. And related to that, we have, I think, unique technology in programming photonic circuits. And in Southampton, we particularly have unique technology in that we have some non-volatile ways of doing that, which some of the other applications suffer from. And finally, we run a foundry service called Cornerstone, which I'll talk a little bit about later. This is not like a commercial foundry. It started off as an academic foundry, but it's sort of got a life of its own, and I'll come on to how I think that we can collaborate on those things as we get there. I just thought I would put a slide in about how the ORC, the Optoelectronics Research Centre that I represent, works with other parties, because I think actually this is fairly common in the way that UK universities can interact with people. So obviously, industry could directly fund a research program in the university. But we have a large number of folks with expertise right across the silicon photonics range. Silicon Photonics at Southampton has a group of 60 people, slightly more than 60 people. Obviously not as big as some of the companies, but it's a large group for a university, and there's a diverse range of skills. So we can do consultancy, we can solve a very specific problem that you may have, and some of the Xanadu problems we could probably address in some ways. Perhaps we can talk later. Cornerstone, I'll come back to, but that's a way of fabricating devices, especially for early stage startups. You can co-fund work that we do with other people. You can get access agreements to come directly and work in our clean room, or we could work on a joint venture with multiple sources of funding. It's important that I mention the clean room at Southampton because this is what facilitates all of this. Now, I mention it really because I have the impression that university clean rooms have a bit of a bad name in the sense that they are often a little bit contaminated, maybe not as well run as you might like. I want to tell you that not all university clean rooms are the same. Not that we are anything like some of the facilities that you will see in some of the large companies in the room, but we work in industry-like processes, so we work at wafer scale. We do things that enable tech transfer and so on. And just to demonstrate that, we currently hold 2 of the world records for integrated transmission in terms of data rate. So that modulator you see there, the top left, it's a photonic integrated circuit with 2 electronic drivers flip-chipped onto the surface. So we designed the drivers. We had these particular ones made at TSMC. And that, for anyone who recognizes the technology, will see that that's 2 drivers forming a PAM4 modulation technique. When we published that, the data rate was 224 gigabit per second. And on the right, it's a particular type of modulator that we drove beyond 100 gigabits per second and on-off keying. But we've done better since, so we can do on-off keying at 182 gigabaud. Now, that means essentially switching the light on and off at that data rate. But for PAM4, we can go even faster, slightly slower gigabaud data rate, but 308 gig PAM4. And if there are any telecoms people in the room, they will tell me that those eye diagrams on the right are terrible. I know that. But I would point to the input signal on the left, which is the electronic signal, which is also terrible. And so it isn't the photonics that's the bottleneck here, it's the signal driver that we get to start with. So we can make the photonics go fast enough and the integration go fast enough, but perhaps, and actually the testing is difficult as well, because we got the best test equipment, state-of-the-art test equipment we could for this technology, and still it's difficult. So, I think there's a discussion to be had about how fast is fast enough and what technologies we use there. I'm running out of time, so I need to get on. So Cornerstone. So we began Cornerstone to open up the facilities at Southampton to other academics in the UK. That was the plan. And that's because, certain universities don't necessarily have fabs. They might have great ideas, but they can't realize them. So we opened up the clean rooms, and we operate a multi-project wafer service for other academics. That was the beginning. And it was just silicon on insulator initially. Demand from the users meant we brought in all these other platforms you see, putting lasers on chip, flip chipping electronics, silicon nitride, different types of silicon on insulator platform, germanium on silicon, and suspended silicon for all the different wavelength ranges and applications. What happened was, it got a life of its own, as I said. And it turns out that part of the reason for that is that startups, for 2 reasons, they tell us, find it difficult to access some of the foundries. And some of that was alluded to earlier. Because the foundries largely want volume. And so if you're at the prototyping stage, it's difficult to get access to a foundry. But also, startups don't necessarily know which foundry is best for them. They don't necessarily want to be locked in, and they don't necessarily want their IP impacted. So we started Cornerstone as a license-free open source foundry. People can use our PDK free of charge. There's no licensing charges. They can use the designs, etc. And we don't impact the IP. And it turns out this is particularly useful for early stage proof of concept and prototyping. And now we have customers in 23 countries. Last year we had more industry users than academic. And we're now part of the Europractice brokerage across Europe. And so none of that was expected, but it turns out that it's because we can help at the early stage prototyping for particularly SMEs, but also academics with ambitions for entrepreneurship and scale up. So I think we have a role to play, in the prototyping stage before people start going to their foundry of choice. And we offer flexibility in training and so And what's happened recently, so part of the semiconductor strategy in the UK, it's been a little bit disrupted because of the election and the change of government and so on. But one of the early investments we secured earlier in the year, before the election, was for a new innovation knowledge center. And that is based around the Cornerstone Foundry, but the idea now is to bring all the players within the UK to be a little bit more coordinated in accelerating progression through the entrepreneurial story. So providing training, linking users with accelerators, putting VCs via the accelerators, training, and hence supporting the commercialization uptake. But the other thing we were able to secure within this program is if you're a UK academic, then you can get subsidized access to the foundry now. And we also have some flexible funding for the academics in the UK to solve industry-related problems. But of course, international users can also use Cornerstone, it's just you don't get the subsidy because it's UK taxpayers' money. Nevertheless, we welcome the interaction. So at the moment, we have 108 partners in the program, but we always welcome more. So I just wanted to give you quickly an example of how, as a university, we might work with industry. So this is an example of a startup. And this is a startup in which I'm a founder, so it's easy for me to use this as an example. So this is a LiDAR company, and their approach is a little bit different from some other LiDAR companies in that they use a focal plane array as the emitting mechanism for the illumination of a field. And so, just as in any silicon photonics activity, we use gratings as the emitter. And so the light comes out of the top surface of the chip. Now, the top surface can be useful for other reasons, for perhaps integrating other things. So they were interested in using a way of getting the light out of the back surface rather than the front surface. And so in a stack, you might use one of the metal layers to do that, like so. So what we can do is do the proof of concept of that process to de-risk it before they go to the foundry and spend an awful lot of money on a tape out in a foundry. So this is an 8x8 demonstration of backside illumination. And the little things you see in the 8x8 are the little emitters. They're coated in a metal so that as a reflector, and that's why they're very clear in this diagram. And of course, we've developed the associated electronics to drive the displays you see on the right. So that proves the concept, and so now they can go to the foundry layout with much less risk of that thing actually working, or rather not working, if I get that the right way around. So it's an example of how a university can work with us to de-risk a particular problem that they have in the prototyping or development stages. Okay, I haven't said much about quantum or indeed AI so far. So do Southampton work in quantum? Well, yes, and here's a few examples of, on the left, a network that's coordinated by Southampton, some work at the top right on some of the specific work. I'm out of time, so I'm going to tell you this very briefly. And then we've just been awarded a Center for Doctoral Training in Quantum Technology in the bottom right, which is essentially a training model for training PhD students. And so the focus is clearly on quantum in this case, and you can see the associated companies in that technology. We also have work in other materials other than silicon photonics. So this is a group led by Peter Smith, and their work is predominantly in lithium niobate. In this case, periodic poled lithium niobate, but for different reasons. We've already heard that quantum is interesting from lithium niobate point of view, not just for the switching, but also for potentially the low loss. Silicon photonics for AI. If I may take an extra minute or two, I'll just tell you about this. So I mentioned parallel processing is a natural advantage of photonics, and here is, just one example of that I've picked out, where the photonics, because you can integrate on chip, you can get a lot of data, a lot of devices on chip, in order to do the processing very efficiently on chip, and that's where photonics, in tandem with electronics, can enhance the technology. And at the bottom there, I'm showing you our unique addressable programmable circuits. I don't really have time to talk about that now. And my last example is talking about the mid-infrared that I mentioned earlier, where we're developing new platforms for guidance. But in this case, it's a use of AI. And it was something that was mentioned earlier by one of the speakers. So this particular application is about trying to identify early-stage cancers. And so in this case, it's a spectroscopy technique. So we take a scan of wavelength, but the scan is complex, and you can't just interpret it by eye. So we use AI to categorize and classify each sample in terms of whether it's cancerous or non-cancerous. And you see on the bottom right the very preliminary data, and that's a tiny sample. So that doesn't demonstrate we've done it. So it looks good, but it's a tiny sample. So this enabled us to get ethical approval to go ahead and do a much bigger sample. But it's promising in terms of not only photonics contributing to the AI technology, but also using AI technology in some of these emerging and important problem areas. I was also asked to just tell you about existing links to Singapore, and some of this was mentioned earlier. Southampton was integral in setting up the Photonics Institute at NTU, so this is a joint institute based around the technologies at NTU. And so silicon photonics is one of those, and so I've spent some time as a visiting professor at NTU, and we've done some very good work there, but there are other aspects of that technology that have been brought in from the UK, notably the optical fiber technology and some of the nanophotonics work. And I'm also part of a very new center that has just been announced but not actually started yet, the National Center of Advanced Integrated Photonics. So I'm an external collaborator on there and delighted to be consolidating our links with Singapore. But actually, going back to the delegation that's here, we think there's a lot more opportunities for a lot more diverse links between the UK and Singapore. And actually not just Singapore, others including Canada. So I'll stop there, and apologies for taking a minute or two too much. I always do, I'm afraid.
Thank you. Shall we give a big hands to Professor Reed for his sharing in that, highlighting the crucial role of silicon photonics, driving innovation across multiple sectors, and paving the way for the next generation of technological breakthrough. Thank you so much. Very insightful indeed. And now it's time for a bio break. We'll take a 15 minutes break, and we'll all be back by 10:50 in the hall for the next presentation and the panel discussion. Thank you so much, ladies and gentlemen. We'll see you in 15 minutes time at 10:50. Thank you. Hi to all our guests. I know time flies really quickly. Sorry to interrupt your conversations. May I now kindly invite all our guests to be back into the ballroom to continue with the next segment. And also, we will be leading up to the panel discussion coming up as well. So at this point of time, I know it's really quick for the 15 minutes just fly past like that. And at this point of time, I would like to encourage all our guests to please make your way back into the ballroom as we continue for the next segment together with the panel discussion. Thank you so much. All right, ladies and gentlemen, it's 11 a.m. We'd like to welcome all our guests to be back into the ballroom as we proceed with the next speaker to speak about AI innovation and also following by the panel discussion coming up next. So please welcome back, everybody. Thank you so much. Welcome back, everyone. I do know, perhaps I'm thinking, maybe the reasons why you're hanging around the outside area because it's perhaps slightly warmer out there than in here. Don't worry, I am aware myself, and we have already informed RWS to adjust the temperature a little bit so that we can all be a little bit more comfortable in here in the hall. Thank you so much for your kind patience. And yes, we are so ready for the coming up next. We have our next session to focus on the pivotal trends on reshaping the AI landscape and the opportunities they present for the transformative growth. So we're excited to hear from a key leader at the forefront of this revolution. Here we have, ladies and gentlemen, please join me to welcome Lawrence Liu, Director of AI Innovation at AI Singapore, as he shares how AI Singapore has built a world-class AI engineering team, leveraging both talent and cutting-edge semiconductor technology in his talk on building an AI-first nation. Ladies and gentlemen, a round of applause, please, for Lawrence.
Okay, morning everyone. So thanks for inviting me to share the next 20 minutes with you on becoming an AI first nation and how semiconductors has played a very, very important role in our mission, in AI Singapore's mission. So my name is Lawrence. I'm the Director for AI Innovation in AI Singapore. And I was given a title to talk about the mega trends shaping the semiconductor industry. So I've added in a number of slides into my usual deck. And obviously I have to remove quite a lot of AI Singapore's information. So for those who are interested to find out more after the talk, feel free to approach me or drop me an email, which you can get my contact from the organizers. So AI Singapore is not new. We are onto our 7th year. I am still employee number 1 of AI Singapore. And it's been a very fun journey, a very wild ride. I'm still enjoying every day. And one question I get asked is what keeps me up at night? It is how do I find more projects with the industry, to help the industry, but also importantly, to use these projects to train more Singaporeans to become AI engineers. So in AI Singapore, we have 5 pillars. Research, which funds professors to undertake cutting-edge research in AI. Technology, which also funds researchers and parts of it to startups to actually build AI solutions through challenges price challenge, technology challenges. AI innovation, which I run, has a little bit more programmatic approach to getting projects executed and building talents. AI products, which I also used to run, I no longer run this. It's all about building AI products for the industry. And the most notable, there are actually two notable outcomes from this pillar. One, which is the latest craze now on LLMs. So for those of you who want a Southeast Asia aware large language model, come to us. Sea Lion is actually built by AI products team. The other one that actually some of you may have already used, we know, is a open source RPA tool called Tech UI. It's very popular. It's been downloaded probably today, nearly over 200,000 times on GitHub. AI governance, we look at the issues around AI ethics and governance, and it's more of a thought leadership play in that pillar. So I always like to share this slide because when you hear, oh, this is AI Singapore, it's another government outfit, it's in the universities, what do they know about the AI industry? Over the last 7 years, we have worked with nearly 1,000 companies. We have approved 179 projects. That means of these 1,000 companies, we have worked with them, distilled down to 179 in this case, and approved their AI projects submitted to us. And of this 179, we have actually completed 110 of these AI projects. I think we are probably one of the few teams in Singapore or in the region that have actually deployed 110 AI projects into production. We have worked with the likes of IBM to actually help them build an AI model to predict which of the items that they are producing previously in the Tampines factory here that may have very high return rates. We have helped Continental to use both natural language processing and computer vision for their QA process, where they verify specifications given by customers against the output, against, in this case, a car dashboard that Continental produces, that specifications meets what has been, or rather what the engineer has prototyped or developed meets the customer's specification. At their innovation day, I think a week ago, 2 weeks, they gave an update on the status of this project. It's been rolled out to a number of their factories globally. And one of the outcomes from these projects is actually 4 patents. This project was done by AI Singapore in 7 months under what we call the 100 experiment programs. Other projects that we have done include for our SMEs like Q&M, dental chain. For those who are in Singapore or in the region, you visit a Q&M dental clinic, they'll do a dental x-ray. The AI system that is running there is built by AI Singapore. It detects your missing tooth, the problems with your tooth, the problems with your gums. A new updated version of it even generates a treatment plan. So from manufacturing perspective, from a semiconductor perspective, we have done a number of projects in manufacturing, and this chart shows you the type of projects that we have done in manufacturing. I've highlighted the 2 most common, which is computer vision, which should not be surprising, and also predictive modeling. We have a lot of projects where manufacturers want to find out when their machinery needs to be replaced or when it's going to fail and so on and so forth. These are real-world data. These are actual projects that have been completed by our team. I know everybody is talking about Gen AI. Let me tone down the hype a little bit. Today, we see probably about 40–50% of our projects is Gen AI. The rest are still very traditional AI projects, like in computer vision, in predictive modeling, in time series prediction, and so on and so forth. This is actually a live board, as in a whiteboard, of our projects. This is batch 16, which has just started their projects probably a month or two ago. Only of 1, 2, 3, of those 6 projects that we have for this batch, only 2 is Gen AI. The rest are our traditional AI, or discriminative AI if you want to be more technical. We have not embarked on quantum AI yet. We hope to do so, probably with the next tranche of funding that we get. Maybe we have to look and work very closely, definitely with the quantum office on this. So in terms of transformation trends, what has actually driven, what has enabled AI to be where it is today? Now, AI has been around for a long time, 70, 80 years. But what has changed the last couple of years, and actually this slide is more than 10 years old. Okay, it's not new. This slide was developed when I was in Revolution Analytics 10 years ago. There was data explosion. Everything is connected. Even as you are sitting here, you are sending data to the cloud. Advanced algorithms. Obviously, today, the last breakthrough in terms of algorithms is the transformer. It's been 8 years old. Since then, there's never been another breakthrough. Every other LLM announcements that you hear every week is just more data, more compute. Hopefully, with quantum, we can get another big leapfrog. But today, it is still around the transformer architecture. I have a picture there of the AI data scientists, AI ML data engineers, because yes, there is a shortage, but the good thing is because this is such a hot area and people are dreaming of a $300,000 prompt engineering job, you get a lot of young folks excited and wanting to come into the industry. So there's actually a lot of talent coming on stream. You just need to be able to identify them, groom them, and bring them into your ecosystem. Of course, the cost of computing has also dropped because of cloud, because you guys there are producing hardware that is faster, better, at a much lower cost. And in the middle there, I have software. One of the big drivers of AI machine learning is open source software, which I know in the semiconductor industry, a lot of your technology is very proprietary, you keep it very close at heart. But a lot of the AI software is open source. Whether is it in the big data space with Hadoop, programming languages like Python and R, and obviously today with large language models from the likes of Bloom, ChatGPT, and Meta. Just to clarify, I have a very good friend in the industry who I say if Meta, Meta's Llama is open source, I'll get scolded. Llama is source available. It is technically not an open source large language model. So because of certain restrictions they have put on the use of it. So how are we in AI Singapore building this ecosystem out? It is not just about the chips, the hardware. It is also about the talent that can use this hardware. And in AI Singapore, we have been building to date 400 highly skilled AI engineers that are distributed across the industry today. Some of them are actually in your organization. Many of them may not necessarily have an engineering or STEM degree. We have engineers who have crossed over from being a CFO. We have ex-lawyers who have all become AI engineers. So we actually train them through the AI apprenticeship program there. Semiconductors are definitely important, and we use a lot of compute powers, right, to run our AI algorithms, our machine learning algorithms, our large language models. We can't get enough. The good thing is that the Singapore government has been very supportive. We have large supercomputing facilities, including not just on-prem, but in the cloud. So this slide shows in a snapshot what we have been doing the last 7 years. Or actually, yeah, the last 7 years. We started with the 100 experiments. And that's the one that you see with the people figures in there, where the industry will come to us with a problem statement. We will evaluate, and like I said, we have worked with nearly 1,000 of these problem statements and approved about 179 of them to date. For every problem statement that we approve, AI Singapore will contribute $180,000 of in-kind contribution, which is manpower. The company must have skin in the game. So you have to put in $180,000 also. And with that, we will assemble an AI team making up of AI engineers, our apprentices, and ML Ops team. They will work on your project full-time. Full-time. Mondays to Fridays, 9 to 6. Many of them stays back beyond 6. Sometimes we know they work over the weekends because we can see them checking their code. It is a full-time effort for 7 months to be able to produce the AI products that I spoke about, from the dental chain to IBM to Continental. The great thing is that under this program, you own the outcome, you own the IP. I'm not interested in the IP. Typically, when you collaborate with the university, it's a joint IP ownership. But in this case, for 7 months, my take is that, yes, there is some IP created, but it's not so much that I want to have a tug of war with your legal. So please, you own the IP. I only want your project to be able to train more Singaporeans. So who are these apprentices? They are Singaporeans who quit their jobs and dedicate themselves 9 months to become AI engineers. And it's not that we take in anyone who raise their hands. Typically, we'll have about 300 to 400 Singaporeans who apply for the apprenticeship program. We have 3 recruitments a year. Less than 10% will get selected. So every batch, we have about 20 to 35 Singaporeans. They would have self-taught themselves Python. They would have self-taught themselves AI, machine learning. They can build a pipeline. They can visualize. They can select the right algorithm. But the question to ask is, if they can do all of that, why are they not in your organization if you are trying to build an AI team? Very simple. Your HR will have filtered them out because they don't have a computer science degree in AI. They don't have 2 to 3 years working experience in AI. These are people who could be engineers, accountants, lawyers, self-taught AI enthusiasts that will fail your HR filter. But when we created AI Singapore, when I needed to deliver 100 AI projects, just like you back in 2017, I needed to go out and hire these engineers. I couldn't find Singaporeans. I had 300 resumes, fantastic. Only 10 Singaporeans. The rest was our friends from all over the world, China, India, Europe, South America. And I said, I cannot be called AI Singapore if I only have 10% Singaporean, 90% foreigners. Today, our ratio is probably 95% Singaporean, 5% foreigners. If you walk into AI Singapore today, in our office, 95% of the people that you see there are Singaporeans. So when you say you cannot find AI talent or Singaporean AI talent, I challenge you, come to our office. You have a job offer, you bring it there, I can guarantee you, you can find an AI engineer. We have lots of great, because you are in semiconductor, we have lots of process engineers, chemical engineers who are trying to exit from the chemical industry. They do not want to become a software engineer and try to compete with the young ones to join Lazada and Shopee. They want to go back to the process industry, semiconductor industry. So these are now process engineers who now know AI. We have many of them in our cohorts. So we find these talented Singaporeans, bring them in, and basically put them through 2 months of deep skilling, and then in the next 7 months, they'll work on your project. And the outcome has been fantastic. Over the last 6 years since we have this program, we have managed to train about 405 Singaporeans. About 50, 60 of them are with us in AI Singapore. For the Singaporean guys here, the way I attract them to join me, because you all know, as within a government program, we can't match the salary of what you can afford. I can't match the salary of a Google or Microsoft. So how do I attract this apprentice when they finish the program to join me as AI engineers? I started with 3. Today we have nearly 50 engineers. I tell the guys, come and do your second national service. So, because in Singapore we have this national service where all guys will have to do 2 years, whether you're in the police or army and so on. So I tell them, and most of them have already done their national service, come and do another 2 years with me. Help train another 3 or 4 batches of Singaporeans. So many take up that challenge. So they join me not because of salary. They join me because of passion. So we are very, very passionate engineers. For the ladies that join us, simple. Come and do your first national service. So we have managed to recruit and retain a very talented group of very passionate engineers who join, who believe in our vision and motivation. Along the way, we also had to create a lot of different programs. You can't really see the text, but I'll describe to you. We have created what we call a generational AI talent development program. It was created not because NRF or MCI at the time said, Lawrence, please create training programs. No. Because when I was trying to talk AI to professionals, to SMEs, to large organizations back in 2017, there was a lot of misunderstanding of what AI was. So we created AI for everyone. 3 hours face-to-face, we did it twice a month and open to the public, free. So through AI for everyone, we reach out to nearly, today I would say, 200,000 Singaporeans already. It's been adopted by the schools, by the civil service, to train the officers. So if you have kids in a school, they would probably have gone through or will be going through AI for everyone because it's mounted onto the school system. Now, through AI for everyone, we have also had the privilege of partnering with some of the organizations here to bring AI into your organization. Now, AI apprenticeship and some of the programs in AI Singapore is about training engineers and PhDs. Why is AI for everyone also very important? For organizations that are trying to embark on AI, which I'm sure all of you here are, don't forget, AI is not about just research and PhDs. If you want to roll out AI successfully in your organizations, you need to make sure the operators, the technicians, the people in the production floor, the people in your office, the admin staff, are fully aware and exposed to AI. If not, I can tell you when you try to bring AI into your organization, try to implement, it will fail. Because they will be afraid of losing their jobs. They will push back, they will sabotage the project. So, even before you try to build that AI team, you must have a strategy, you must have a way to educate everyone in your organization on what exactly is AI. We have learned this through the hard way. We have done many projects with organizations that we had pushback from the workforce because they were afraid they will lose their jobs. And therefore, today, one of the things that we talk to organizations about, if you want to do AI, do you have a strategy from management to bring AI to everyone in your organization? That must be one of the things that you must think about. Not about hiring the top PhD, not about hiring an AI engineering team, but how do you make sure everyone in your organization is AI aware? So with that, we hopefully we can train up the whole Singapore workforce to be AI aware. We have our AI readiness index if you want to find out how mature you are in terms of your AI readiness. It's only 12 questions. You don't need a McKinsey or Deloitte to help you with that. In fact, one of the big four actually use this to benchmark their own internal departments. Just 12 questions. Just go to aisingapore.org/ARI, A-I-R-I. You'll find out how ready you are as an organization or department in terms of AI maturity. And obviously, underpinning all our projects is semiconductor. So about 25 meters away from my office where I sit is Singapore's supercomputer, largest supercomputer. Right? We have access to that. We use that when required, if we need capability class computing to be done. If not, we'll run it off smaller machines that has a couple of GPUs or the cloud. So with all this experience that we have built, we have even productized this program into handbooks, manuals that we are more than happy to share with organizations so that you can replicate what we have done. We have even put together an org chart on how you can build a team. It should be an extension of your L&D team, but preferably part of your engineering team, right? To actually build this AI talent or quantum talent. You can replace AI with quantum, it will be the same. Who has used this? Egypt signed on to use this 2021. Malaysia has signed on to use this. We are currently working through the exact T's and C's for Island of Man, who's keen to leverage this program. And by Switch in October, we'll be announcing another 3 countries that will be using our programs, whether it's the 100 experiments or the apprenticeship program. One from Eastern European, one from Middle East, and one from Africa. But keep in mind, all our programs, when we created this, was actually not designed for countries to adopt. It was my intent to help large organizations in Singapore to replicate what we have so we can get more local talent trained in AI. But the people who found this really useful were some of the national agencies in other countries. So this is my last slide. How many of you actually use Copilot or Gemini on a daily basis? Can I have a show of hands? So if you have not used, you need to start using. It is not just about productivity, it is very transformational. How many of you here, I'm sure a number of you, have written a book? How many of you have written a book? And how long did it take you to write your book? A year? 2 years? 18 months. I wrote this book in 3 months. I did not use Gen AI to generate the book. That would be cheating. I used Gen AI as an assistant. I prompted Gen AI to say, you are my biographer. Ask me questions about the AI Singapore program. I fed an initial deck of slides and documents and websites to the Gen AI and said, review that and now start asking me questions about my AI Singapore program. For an author to sit down with a white piece of paper and blank piece of paper to start writing is very, very difficult. But when someone asks you a question, everything is here. It's very easy to articulate that. And that's what I did. So I spent 5 to 6 sessions, 30 to 40 minutes each time, locked up in my study to start talking to the computer, to articulate the AI Singapore story. And after that, I basically have the whole content done in a month and a half. And the rest of the 1.5 months was really formatting and trying to get it published on Kindle. So if you have not started using Copilot or Gemini, please pay for it. It's only $20 a month. I paid for this myself. NUS did not pay for it. Because large organizations, to get it approved by your CIO, CEO, CFO will take forever. It's only $20 a month. Those of you all of you are sitting here, you can afford that. Pay for that version that will protect your data, start experimenting with it, and see what you can use it for. It is beyond productivity. You're only limited by how crazy you can think, how creative you can be in leveraging technologies like large language models. Thank you.
Wow, thank you so much, Lawrence, for sharing. Very interesting, very insightful indeed. I would love to hear more, and thank you for remaining on stage because we need you for the panel discussion as well. Right, so yes, we are moving on to the panel discussions, as I do know we have burning questions for our previous speakers earlier on. So without further ado, let us welcome them on stage. We have, moderating this discussion is Richard Wong, Senior Vice President and Global Head of Security Market Advisory at Frost & Sullivan. And join him with a panel are distinguished leaders. We have Ling Kiok Tong, Executive Director, National Quantum Office, Rafael Janik, COO, Xanadu Quantum Computing. We have Professor Graham Reed, University of Southampton, Lawrence Liu, Director of AI Innovation, AI Singapore. So indeed, this is a key session of the panel discussion that brings together experts to explore the strategic integration. As we talk a lot about AI and quantum this whole morning, isn't it? So how does this bring into the global semiconductor industry? So before we begin, a general reminder, the QR code is in the booklet itself, the QR code that leads you to Slido. It's a platform that we, SSIA, always use for the Q&A. So if you have any questions, do scan the QR code, enter, and that's where you can put in your questions. You can also upvote the questions with a thumbs up so that we know what questions to focus on for the gentlemen. You can find the QR code on the table, the link that links you to the Slido. So give them probably about 30 seconds to get them into the Slido platform. So feel free to, because during the discussion, I'm sure there will be a lot of burning questions. Just get the questions in, our moderator will take a look and to find an appropriate time to address these questions on the topic itself. All right, thank you so much, everybody. I think we are all good. Perhaps they need some time on their phones to get into Slido. All good, all right. And I think if you're ready, maybe we can hear your applause. Please, to welcome our panel discussion for the day. Looking forward for the insightful discussion.
So, good morning, everyone. So great to be here today in this session to meet up with our industry participants from the semiconductor industry. I think in the panel with me are really the experts. Yeah? Myself, I'm more focused on the business strategy, looking at the technology roadmaps, helping customers to look at some of the business challenges that they face. But our people here, they are the policy expert, industry experts, technology experts. So I sincerely hope that you will actually get onto Slido. Please feel free to ask any question, and I think our esteemed panelists will be more than happy to address those questions. Yeah. So with that, maybe what I'll do is I'll just start off with a soft curveball, yeah, right, to our panelists. My first question is that you have talked a lot about AI as well as quantum computing today. Yeah, but how do you actually see the semiconductor industry evolving over the next 5 to 10 years with these advancements in these technologies? Yeah. So anyone would like to take the first shot at this?
I'll never be shy, but you might have to stop me from talking too much.
Sure.
I do think that right now in quantum, we're starting to rely pretty heavily on the semiconductor industry to solve some of our most challenging problems. And I think there's a really big question right now from many semiconductor players on when and how large will the quantum market be. I think in the past there's been a few instances where the semiconductor industry has thought that there was going to be the next great thing. They've started building capacity with maybe that not coming up. Maybe silicon photonics has had that once or twice historically. So what I'm hoping for the future of the semiconductor industry is that we do start focusing on quantum projects now to de-risk it being funded by great government initiatives like Singapore's quantum strategy, to fund projects allowing both the quantum startups as well as large semiconductor companies to engage with very low risk to them. And they begin building out that supply chain that is going to be required to deliver on quantum. I think there's a really big opportunity, not just for industry, but also for national governments to actually build and become major players in this up and coming supply chain. And it's not only semiconductors, they're definitely a major part of that, but there's a lot of advanced manufacturing that is going to be required to actually support that.
I think what the quantum industry needs is a ChatGPT moment. And when that happens, I think everyone here will be scrambling to build quantum components and quantum systems, like what some of the GPU players are struggling with meeting the supply chain. So I think if we, hopefully Singapore, can create a application or create that ChatGPT moment, I think that's where I think we'll see a quantum leap of use cases and demand.
For more than 17 years, and we also have a large ecosystem of across the universities, NTU, A-Star, SUTD, who can work with us jointly as a national effort to make sure that we have the capabilities to do a full stack quantum computer over time. So this is an ambition, and we will continue to move down that path as well. Yeah.
Cool, thank you. So I'm going to ask a question that's a bit more open to anyone who can respond. It's a big challenge that I think some of our industry participants are actually facing today, because there's this east and west tension, and hence there is definitely going to be a bit of a race between different parties to look at quantum or even AI supremacy, right? So what are the geopolitical implications in terms of all these advancements, and what are the impact on the semiconductor industry? Should they look at where they should hedge their bet? Should they look at building up their robustness in terms of their supply chains? What can they do to try to anticipate and prepare for this competing fronts, that is going to happen within these advanced technologies, with these advanced technologies? Yeah. Anyone want to step into that?
We tend to be very apolitical as an organization, but there are realities about the fact that we're located in North America, the fact that a lot of our funding comes from Canada and the US, and it does limit which partners we can work with internationally. And I think the more interesting for us thing that's happening now, it's not so much around maybe the race or the competitive side, but it's around how much countries are now reinvesting in the semiconductor industry. So South Korea has dropped billions of dollars, I believe hundreds of billions of dollars in their semiconductor refresh. We see similar initiatives in Japan, huge photonics fabrication facility going up in Spain, funded by the EU. The US CHIPS Act is also quite substantial. Even Canada, to a much smaller degree, but is trying to do a refresh of their semiconductor strategy. So for players like ourselves, with our partners right now, it's honestly more of a question of where should we do business? Because for all these projects that we're running, we are getting support from various governments, and the big question becomes, where should we plant ourselves? And it's not something we've been able to answer to date.
Okay.
I guess from AI Singapore perspective, in a way, this tension has sort of helped in my team's KPI, because today we have actually quite a number of Chinese companies that have relocated their R&D teams into Singapore. And I would say we are increasingly seeing a lot of the Chinese AI companies coming to us to say, hey, we want to do joint projects, we want to do the 100 experiments, do you have apprentices we can hire, and so on. So in a way, it has benefited. In fact, I was just interviewed, I think, last week by Zhao Bao, because NTU announced their collaboration with I believe it was Alibaba, extension, right, of their collaboration. And I say, well, both East and West, I think there are talents, there are technologies, and from my AI innovation perspective, from my 100 experiments, from my apprenticeship programs, we will learn from both. We were happy to do projects with both. Ultimately, if there's a project that can allow me to train more Singaporeans, there's a project that can help a Singapore company, from AI Singapore, from AI innovation perspective, from my team's perspective, it's a win.
Okay.
It's a very difficult question because I think it's not clear how things will evolve. But I think there are some positives and clearly there are some negatives. One of the positives is the recognition that there are not enough trained engineers. And so investment in training will increase, and participants of all areas will get involved in that. And some of the negatives have been alluded to about who we can work with. I don't see where that ends because it's much more of a hindrance than a help. What I've observed, though, I think Singapore seems to find itself in a unique position, and actually could help in many ways, because it seems that you can somehow work with both groups, and if you can leverage that in a more positive way, perhaps there's a strong outcome. And I think everyone wants to see at least the technical people anyway, want to see a more positive resolution.
Okay. Anything to add? No. Okay. So I think what I'm going to do is just ask one more last question from my side. If the audience has any other question, please do put it into Slido. If not, then we will just end about 5 minutes earlier. We are actually a bit delayed from lunch, but so my last question is very simple, right? What should the audience do after today's conference? Because we know that quantum computing is coming. Now, what is the messaging they should bring back to their colleagues, to their bosses, to their stakeholders, when it comes to quantum computing?
Maybe I can start first. I think this is a conversation I had with Wee Sing. I think arising from today's talk that I was sharing with you about some of the possibilities that the synergies that the quantum industry can have with the semiconductor industry. Those are possibilities, but we really need to put some concrete details into what these possibilities turn out to be in terms of collaboration. And I really look forward to working closely with SSIA to maybe form some focus groups around some of these topics of interest that will allow us to dive deeper and work out some of the concrete problem statements that we wish to solve from a quantum industry. And then also from a quantum industry, our ask of the semiconductor industry of how it can enable us. And from those discussions, it can then fit into our what we call national level quantum programs. Things like the National Quantum Federated Foundry, NQFF, or our National Quantum Computing Hub, or even our National Quantum Safe Network. So I think the pathway is quite clear, at least from my point of view. Yeah.
Okay. Thank you. Anyone to add on?
Can you just remind me what the question was? Was it about what should...
basically, Singaporeans, I think we are very practical, right? We come for conferences, we learned a lot. But at the end of the day, what should we do next based on what we have learned today, right?
I thought that's what you said. I just thought I'd clarify just in case. Well, okay, I would say this, wouldn't I? But without the technology, you can't implement anything. So if you're worried about what to do next and where to go, I would say consolidate the technology, consolidate the infrastructure. I might be talking to my own government here, in that the infrastructure and the areas in which you are clearly expert need to be retained and supported. But silicon photonics is clearly here to stay. It's impinging right across semiconductors, right across these applications. And so everyone should do silicon photonics.
I'll support that.
I guess for me, it'll be more from an AI angle. Like I mentioned, find out your AI maturity if you are beginning to look into your AI journey, right? The AI Readiness Index. Checked out AI Singapore website on the programs that we have, especially the 100 experiments. If you are thinking of hiring AI engineers, like I say, we generate 25 to 35 AI engineers every 3 to 4 months, right? So there's no shortage. And maybe it's, maybe I'll go to Kyok Tong to say, hey, let's do quantum for everyone. And then maybe in 6 months or a year's time, send all your staff to the Quantum for Everyone online program.
All right.
Look forward to that, Lawrence.
All right, thanks. Thank you. All right, again, I think we should give a round of applause to these analysts for their views. It's been a very interesting session. I think I've learned a lot from both your presentation as well as some of the conversations that we have had. I hope the audience had a good takeaway today because personally, I feel quantum computing is really going to be a disruptive technology. Yeah. Sorry to misuse the term, but it is really a disruptive technology. It's totally different from classical computers. It is a key enabler for AI. It's going to make a big difference. The question is whether quantum computing, whether you become commoditized. Yeah? What's the model is going to be? Will we literally see ever the day where I'm still around, where we have a personal quantum computer? Never say never, in view of our technology, yeah, but it is going to transform the world. So thank you again for your sharing, and I hope, we will hear more from you soon. Yeah, thank you.
Thank you so much. Shall we give a big hands to Richard as well for moderating this panel discussion? Thank you so much, Richard. Thank you once again to all our panelists. It has been really insightful, a lot of takeaways, learning points, and sparking a lot of ideas already. Very inspiring indeed. Thank you so much. And I'm sure we can't wait to catch each other during lunch, isn't it? To catch our panelists, to catch each other networking. It's time to network, indeed. It's time to fill out our tummy. All right, ladies and gentlemen, I shall not hold you up. We're going to have our lunch and be right back by 1:25 p.m. By 1:25, we're going to start off at 1:30 p.m. sharp for the next segment. So if you'd like to also give us some feedback, we have our QR codes outside the ballroom or on the table. Do give us some feedback as well. All right, thank you so much, everyone. We'll see you later at 1:25 p.m. Thank you. Hi to all ladies and gentlemen, welcome back. Please be seated back into the ballroom as we're going to commence the second half of today's summit in a minute's time. Thank you. Hi everyone, welcome back. Hope you're feeling good after you have filled up yourself. All right, just before we kickstart the second half, may I just take this chance to get you to touch your mobile phones, to hands on to your mobile phones, to scan the QR code, because we would love to hear your feedback on the overall summit that you experienced so far. So at this point of time, I'd like to encourage our guests to perhaps scan on the QR code, that little QR code on the table that will lead you to many links with that QR code. And one of it is the feedback form. There's a very short feedback that we really appreciate if you could just take a few seconds of your time right now to just fill out the survey form for some feedback. Really appreciate that. Thank you so much.